So remember, our recurrence relation here is t of n equals 2 times t of n minus 1 plus 1, and t of 1 equals 1. So even if you didn't understand any of that Towers of Hanoi stuff, focus in on this particular recurrence relation. T of 1 is 1. What's t of 2? It equals 2 times 1 plus 1 is 3. How about t of 3? Well, it's 2 times t of n minus 1. That's 6 plus 1 is 7. T of 4? It's 2 times 7 is 14 plus 1 is 15. Great, so we could conjecture by looking at this pattern that t of n equals 2 to the n minus 1. This turns out to be correct, so here's a simple formula for this particular recurrence. T of n equals 2 to the n minus 1. How do we prove that this is correct? Well, we're going to use induction. So let's prove that t of n equals 2 to the n minus 1 by induction. So the base case would be t of 1 equals 2 to the 1 minus 1. This equals 1. And that's good because we had said that t of 1 equals 1. So now we need to prove that t of n plus 1 equals 2 to the n plus 1 minus 1. And what do we know? We know by definition that t of n plus 1 equals 2 times t sub n plus 1. T sub n, using the inductive hypothesis, is 2 to the n minus 1. So this simplifies to 2 to the n plus 1 minus 2 plus 1, and we get 2 to the n plus 1 minus 1. So this is exactly what we wanted to prove. We proved that t of n plus 1 equals 2 to the n plus 1 minus 1, and so that completes the inductive step. Let's do one more example for recurrences. So in this problem we have a vending machine and it accepts $5 bills and $1 bills. And we'd like to know how many different ways can we insert n dollars into the machine. So if you first insert a $1 bill and then a $5 bill, so if you go $1 and then $5 into the machine, that's different than if you insert a $5 bill and then a $1 into the machine. So order matters as to how you're inserting these dollars into the machine. But I want to know, given n dollars, how many different ways can I insert n dollars into this vending machine? Okay. So let's write a recurrence for this. So let's let a of n be the number of ways to insert n dollars. Okay? And a of 1 is going to be 1. There's only one way to insert $1. That's by inserting one $1 bill. How about in general? Let's say I want to insert n dollars into this particular machine. Well, I have two initial steps that I could take when I need to. So I have n dollars in my pocket. I have two initial steps. So first of all, I could insert a $1 bill into the vending machine, and then I would have to insert n minus 1 more dollars into the vending machine. So if I insert a $1 bill, there are going to be a n minus 1 ways to proceed. Or I could insert a $5 bill into the vending machine, and then there would be a n minus 5 ways to proceed. So this term corresponds to the first step being insert a $1 bill, plus it's the number of different ways to insert n dollars, so I could have started with a $5 bill, and then I'd have to complete the number of ways to do dollars into that machine in a of n minus 5 ways. So we get a of n equals a of n minus 1 plus a of n minus 5. That's the recurrence we were looking for. Now, just like when we do proof by induction, when you see a recurrence that has n on the left-hand side and n minus 5 on the right-hand side, you're going to need 5 base cases. So we have a1 equals 1. We know that a2 equals 1. There's only one way to insert $2. I can't use a $5 bill. I have to use 2 ones. Same with a3. I have to use 3 ones. With a4, I have to use 4 ones. And then we get to a5. A5 is 2, right? I could either insert 5 ones or one $5 bill. Now that I have my 5 base cases and my recurrence, I've completely specified this particular sequence. Why again did I need 5 base cases? Well, imagine that I'm trying to figure out what A5 is, and I try and use my formula. It says A5 equals A of 4, okay, that's fine, plus A of 0. But we never defined A of 0. This doesn't exist, so we really needed to specifically specify A of 5. So that's why we needed all of those base cases. In the coming lectures, I'm going to show you how to take a recurrence relation specified this way and a bunch of base cases and actually come up with a simple formula to calculate explicitly what A of n is, like A of n equals some simple formula of n. And so we'll be able to take these counting problems and really simply solve them using recurrences and our machinery for solving recurrences.